Welcome to the second day of 8.2 Integration by Parts. Today's focus is, first, we're going to look at a few examples where you would need to determine if you need parts or not, and then we're going to focus on trig functions today. So I'm going to give you about 30 seconds in this example one, and I want you to determine which of the following should use integration by parts and which ones don't need integration by parts. So take a look at these four right here and circle the ones where you would need integration by parts. Okay, did you figure it out? Hopefully you recognize, just like the example from yesterday, we need parts when we're integrating natural log of x. Do we need parts for the second one? No, this could be a straight U substitution. If u is ln of x, then du is 1 over x. So this is strictly straight up U substitution portion. This third one, the integral of x cubed times e to the 2x, yes, we will need parts for that guy, and we will also need parts for this last one. So how'd you do on those? Were you able to determine when to use parts or not? Next, we're going to look at finding the derivatives of inverse trig functions. And if you remember, we were able to use triangles before. So we're going to first work on the arc sine of x, and then I'll see if you can do the other two. Okay, so remember, if we have arc sine of x or inverse sine of x, if we just set it equal to y, okay, and now we solve for y, solve for x. So that means x is equal to the sine of y. We can create a right triangle where y is our angle. All right, so if the sine of y equals x, then we could label the opposite side as x and our hypotenuse 1, and then using the Pythagorean theorem, we could get this third side. So now if we take the derivative with respect to x, we get 1 equals, the derivative of sine is cosine, and don't forget times y prime. So now we just solve for y prime because we want to find the derivative of arc sine of x. So we divide by cosine of y, and now we refer to this triangle up above. So the cosine of y is equal to the square root of 1 minus x squared over 1, but we don't need to write that portion of it. So we get the derivative of arc sine of x to be 1 over the square root of 1 minus x squared. I want you to use this same process for examples B and C, finding the derivative of arc secant or inverse secant of x, and also for the arc tangent of x. So go ahead, try those two on your own, and then check back here when you are done. Okay, how'd you do with the inverse secant of x? Hopefully you were able to work it through. So if we set it equal to y, and then we solve for x. So x is equal to the secant of y, drawing our right triangle, where y is our angle, we could go ahead and label our side. So the adjacent side is 1, hypotenuse is x, so using the Pythagorean theorem, we get that third side. Now taking the derivative with respect to x, we get 1. The derivative of secant is secant tangent, don't forget times y prime. Solving for y prime, we get 1 over secant tangent. Now, using our triangle, we're plugging in for secant, and we're plugging in for tangent, all right? And we get our final answer there. Then for arc tangent of x equals y, or inverse tangent, remember those are interchangeable there. Solving for x, we get x equals the tangent of y, setting up our right triangle. All right, if tangent of y equals x, opposite side is x, adjacent side is 1, we can solve using the Pythagorean theorem for the hypotenuse. Derivative with respect to x is the derivative of tangent is secant squared, don't forget times y prime, so then y prime equals 1 over secant squared. Substituting in, secant is the square root of 1 over x squared using our triangle, but we need to square that because it's secant squared. And so we get the derivative of arctangent of x as 1 over 1 plus x squared. Now, you don't necessarily need to memorize these three. This is just reminding you we could always, through brute force, use these right triangles here, set those up to get to what those derivatives are. If you memorize them, that just makes it a little quicker, obviously, but if you don't memorize them, we could certainly work through it by setting up a right triangle. So that was more or less review of finding the derivative of those trig functions. Now let's get back into integration by parts, and we will probably be using these trig functions. Okay, this first example is integrating the arctangent of x dx. So we don't know what the integral of the arctangent is, but think about what we just did above. We do know the derivative, right? We just figured that out. So maybe that's going to help us, and we probably need to use parts. So what I want you to do right now is I want you to think about what's going to be your u, and then what's going to be your v, your dv, and go from there. So give it a second, try it, and then check back. Okay, so thinking about what we just did above, we could let u be the arctangent of x, or inverse tangent. Okay, so then du from up above is 1 over 1 plus x squared dx, which leaves the only other part for v to be is dx. So then integrating dx, we just get v to be x. So using that parts formula, we have the arctangent of x times x minus the integral of v du, so x times 1 over 1 plus x squared dx. Now, what we know, or what we should notice here, is we could use a straight U substitution to integrate this portion. So if u is 1 plus x squared, then du is 2x. So now integrating this portion, we still have that x arctangent of x minus that 1/2 times the integral of 1 over u du. Integrating 1 over u, we know it's ln. I just substituted back right away for the u, and we get our final answer, and don't forget plus c. Okay, this next example, we are integrating x times the arcsine of x squared dx. Now your initial thoughts might be to use a U substitution where u is x squared, so then du is 2x. But that would leave the arcsine of u, and we don't know how to integrate inverse sine. Okay, so what that means is we need some parts. And since we don't know how to integrate arcsine of x squared, that's what we're going to let u be in our parts formula. So if arcsine of x squared is u, or we could talk about it as inverse sine of x squared, then du, don't forget this is our chain rule aspect. Okay, so it's 1 over the square root of 1 minus that value that's inside the parentheses. So in this case, it's x squared squared. But then we have to take the derivative of inside that x squared. So that's where we get the 2x from. Okay, dx. So just cleaning it up, we get this equation here, 2x over the square root of 1 minus x to the 4th dx. So that leaves the other portion for dv to be x dx. So then integrating x dx, we get v to be x squared over 2. So now using our parts formula, we have inverse sine of x squared times our v, x squared over 2, minus the integral of v, x squared over 2, times du, so 2x over the square root of 1 minus x to the 4th dx. Okay, I want you to clean this integral up and see where we can take it from there. All right, so I'll give you a second to do that before I continue on. All right. Okay, so hopefully what you recognized is when we clean that up, we have the integral of x cubed over the square root of 1 minus x to the 4th, because those 2's will cancel. So if we do a straight U substitution here, it will work out. U be the value underneath that radical, so 1 minus x to the 4th. So then du is going to be negative 4x cubed dx. So now when we go through and we integrate this guy, make sure to change that minus the integral to plus, because we've got this negative 1/4 that we're pulling out, times the integral of u to the negative 1/2. So going through, And cleaning everything up, integrating u to the negative 1/2, we get 2u to the positive 1/2. Don't forget our plus c, and now we make our substitution back to get our final answer there. Okay, so now let's take a look at this next example here. So I'm actually going to zoom in over to the right and just show some aspects here. So this is the original problem where we want to take the integral of secant cubed of x. So we need to figure out, well, one, we don't know how to integrate the secant cubed of x, right? So there's kind of a few options here. If we let u be secant squared, all right, then we know how to take the derivative of that. That's going to be 2 times secant tangent dx. Okay, well, that would leave us with an extra secant dx for our dv. And that means our v is the natural log of the absolute value of secant plus tangent. That seems very complicated. So it's not necessarily the most ideal aspect. And the reason being, because eventually we would have to take the integral of ln of secant plus tangent, right? And this 2 secant tangent x dx. That's going to be crazy. So what can we do? Well, to make it a little easier, I'm going to kind of show everything and walk through it all and zoom in. To make things a little easier, if we let u be secant of x, then du is secant tangent. If dv is then what's left over, secant squared of x dx, then integrating that, we know how to do that, and it's much nicer. It's just the tangent of x. So v is the tangent of x, okay? All right, so now we can kind of go back over here and zoom in on the problem. Okay, so substituting in, u is secant x, v is tangent x, minus the integral of v du. So tangent times secant tangent of x. So if just cleaning this guy up, we have the integral of secant tangent squared. Okay, well, this is going to lead us into some trig identities, okay? Because right now this isn't helping us. So what can we do? Well, going into our trig identity folder or part of our brain that it's back there, you have to unlock that. Our trig identity is tangent squared of x is really secant squared minus 1. So that might help us, all right? Let's see how that does help us. So if we substitute that back in, where does that lead us? All right, so distributing that secant to both of those guys inside, and then I'm splitting up that integral. All right, so we get minus the integral of secant cubed dx, secant times secant squared, a negative times a negative, that's why we have to change that to a plus the integral of secant of x dx. Okay, now what we should notice, and this is kind of like that last example in the previous day video, this is like a recursive portion where what we get here is this integral is the same as what we're actually trying to find. Right? We're trying to find the integral of secant cubed. So what we can do is now add this portion to the other side. So we really get 2 times the integral of secant cubed dx. And now we're just left with secant tangent of x plus the integral of secant of x dx, and we can take the integral of secant of x. Okay, so this makes it much easier, even though the process here didn't seem so straightforward. Okay. All right, so now we have 2 times the secant cubed of x equals secant tangent. Integrating the secant of x, we get ln of secant plus tangent. Don't forget your plus c. And now just to get this guy all by itself, we have to divide every term by 2, and that's where we get our final answer from. So this is definitely a trickier problem for sure. I wouldn't worry too much about one specifically like this where we maybe have to use a trig identity, but this certainly could show up again. If you have questions, let me know.